In the first part of chapter 9, we were looking at basic concepts around energy, heat, temperature, and the concept of specific heat and measuring heat changes in processes using calorimetry. The rest of this chapter we're going to devote to answering or addressing two important questions: how far a reaction will proceed and how fast that reaction will go. So our list of learning objectives will talk about the concept of dynamic equilibrium, and we can address that using rates of reaction, both forward and reverse. Then we'll learn how to write an equilibrium constant expression, and then use those expressions to predict concentrations of reactants and products. Moving on, we're going to apply Le Chatelier's famous principle that allows us to predict what's going to happen to a system that's at equilibrium when you do something to upset it. And then the last part we'll look at briefly at some aspects of rates of reaction, what a rate of reaction is, and briefly describe the factors that affect it. So equilibrium. In some cases, you mix the reactants together and they turn completely into products. If you think about burning natural gas on a stove or a furnace, all the products become carbon dioxide and water. But that's not always the case. So equilibrium occurs when a system of molecules has reached what we call the lowest energy state. When it's in its lowest or most stable state, it doesn't really want to go anywhere. So one important concept of equilibrium that is not a static event. A reaction at equilibrium will appear that it's just sitting there doing nothing, but actually things are going on all the time, but the net result is no overall change. So an important principle in a dynamic equilibrium, that there are two processes going on in opposite directions, what we call the rate of formation of the products in the forward direction is equal to the rate of formation of the reactants in the reverse direction. When those two rates are equal, overall, there's no net change, even though molecules are changing all the time. And finally, Le Chatelier's principle allows us to predict how a system that is at equilibrium responds to certain changes, and we'll go over those changes in turn. So equilibrium, a rate of reaction perspective. So let's say the forward reaction, our typical kind of general equation, A plus B goes to C plus D. So you start with all A's and B's and no C's and D's, and then you monitor how they change over time. Well, in the graph on the right-hand side are A's and B's. In this specific case, are hydrogen and nitrogen, so their concentrations are starting at a high point. And the product here is ammonia NH3, and this is actually a map of what we call the Haber process, an important reaction for predicting, or sorry, not predicting, but producing ammonia from atmospheric nitrogen. So in this case, we start with N2 and H2 and no NH3, and we map the concentrations over time. The product ammonia is increasing, and the concentrations of the reactants hydrogen and nitrogen are decreasing. But at some point, they come to what we call equilibrium. You know, the concentrations are fixed, static over time. And now we can look at the reverse reaction, where if we take the C plus D's and start with all those and no A plus B's and monitor what's happening, we can plot a similar graph. So our specific example, again, the Haber process, but this time going in the opposite direction. So in this case, we start with all ammonia and 0 H2 and N2 and allow the reaction to proceed. In this case, the reactant ammonia decreases over time and the products N2 and H2 increase over time. But again, they come to equilibrium and those concentrations no longer change over time. So that's the idea of equilibrium, concentrations fixed over time. Just note that the positions of them, the relative concentrations, whether we started with H2 and N2 only, or started with NH3 only, whichever way you start, you finish at the same spot. So you know that the relative concentrations are the same in both graphs. So what we can summarize is that the equilibrium results when the rate of the forward reaction equals the rate of the backward reaction and the concentrations of all the components remain static. So that's the concept briefly. Now let's have a look at how we can express that in a mathematical form. So in our general equilibrium expression, we'll put in the coefficients for the components. So the little letters represent the integer coefficients, just like we did in the past. So this is the overall idea of the equilibrium constant expression. We normally use capital K, and if you like, a little EQ to say equilibrium, but that's not really necessary. And then we write this expression. So the concentration, in this case, we're going to be using molarity terms, but you're also able to use gas pressures as well. But we're going to focus on molarity in all our work. So the concentration or molarity of each component raised to the power of the coefficient in the balanced equation. So that the C in square brackets here represents molarity, and this little exponent here is the coefficient in the balanced equation. So the concentration of C raised to its power of its coefficient, concentration of D raised to its power, divided by the concentrations of A raised to its coefficient and B raised to its. So overall, just remember the way around. The products are on the top, the reactants are on the bottom. And each concentration is raised to the power of its coefficient. So again, it's important to use the balanced equation to make sure the coefficients are correct in order to write the correct expression for K. And always products over reactants. So that's the general idea, how to write an expression for K. So just to emphasize, products over reactants. So in that particular example, we were assuming that every substance that was written in the equation is included in the equilibrium constant expression, but it's not quite as simple as that. So in heterogeneous systems, meaning that there are substances in different states, then not all of the substances, products or reactants, are included. How do you know? So the basic rule of the game is ignore all the pure solids and liquids. So when you're writing the equations, it's also important to represent the states. So remember there are 4, and this equilibrium is chosen to include all of them. So the MnO2 is an S, the HCl is an AC, the MnCl2 is an AC, the Cl2 is a gas, a G, the H2O is a liquid. So remember this rule, ignore all pure solids and liquids. So if I'm looking at my equation, the MnO2 is an S, a solid, the H2O, L is a liquid, and they should not be included in the expression for K. So let's rewrite the equation highlighting the S's and the L's, and everything else that remains would be included. So when I write my expression for K, again, it's products on top, reactants on the bottom. I'm excluding the S, I'm excluding the L. And again, the same rules apply. So these both have a coefficient of 1, so their exponent is 1. The HCl has a coefficient of 4, so it's molarity of HCl raised to the power 4. So expect to be asked questions to write equilibrium constant expressions, and be on the lookout what states the reactants and products are in, because not all of them are going to be included. So just to emphasize, leave out the S's and the L's. And again, the coefficient of 4 means that the molarity of HCl is raised to the power 4. So that's basically the essence of how to write a K. So what does the value mean? Well, it's kind of in a qualitative way. The value of K indicates the direction that the reaction favors. So a large value of K means that products are favored over reactants. And in this example, so we've got SO2 react with oxygen to make sulfur trioxide. So this has a large value of K, which means that the SO3 is preferred over the SO2 and the O2. You think about the expression, the SO3 is on top, SO2 and O2 are on the bottom. So a large value of K is going to indicate that the numbers on the top must be bigger than the numbers on the bottom. And again, it doesn't matter where you start with all SO2 and O2 or all SO3. The reaction goes forwards or backwards. You always end at the same place. So small k suggests the opposite. So in this example, the concentration of CoCl2 at equilibrium is much larger than that of CO and Cl2. So these are the products. The CoCl2 is the reactant. The numbers on the top are going to be smaller than the number on the bottom, consistent with K being small. And again, it doesn't matter whether you start with all CoCl2 or all CO and Cl2. The equilibrium is blind to where it starts. It only cares about the relative concentrations at equilibrium. So, just to test our understanding, this is actually the equation for the Haber process reacting nitrogen with hydrogen to make ammonia. What are these for would be the correct expression for K. Pause the slideshow and I'll reveal the answer on the next slide. And the correct answer there was D, products over reactants raised to the powers of their coefficient, so NH3 squared, H2 cubed. And though it's products and not sums, and it's exponents, not multipliers. It's not 3H2, but H2 to the power 3. So just to remind, it's products over reactants. H2O, which is an L, is not included. Na2CO3, which is an S, is also included. So that's what the correct K expression should be. Writing Ks. What can we do with them? So there are basically two levels of calculation difficulty in working with K expressions. We're only going to look at examples of problems of the first kind that do not involve complicated algebra, but simply substituting numbers in, possibly on occasion having to take a square root, but nothing really more complicated than that. So let's look at a typical example. So in this reaction, we got 2HI on the left and H2 and I2 on the right. You're asked to determine what K is given the following concentrations as shown. So your first task will be to write the expression for K. Remember, it's products over reactants, HI squared. Now sometimes the same equation might be written in reverse. What if you had the example H2 plus I2 on the left-hand side and HI on the right? Then you'd have to remember to invert the expression for K because you flip-flopped the reactants and the products. So don't just base it on memory. Always make sure you write your K based on the reaction that you are given. So now it's a simple matter of putting in the numbers. So the H2 and the I2 in this case are equal, and equal to 1.72 on top. It's 0.54 squared on the bottom, and that's our answer, 10.2. Now I know that very often students omit the exponent. I'm going to say the majority of mistakes come from leaving that important exponent out of the expression of K. Of course, if you don't include it, you're going to get the wrong answer. So let's have a look at this one in a little bit more detail. So I got my N2O4 G on the left, NO2 G on the right, and I'm given the value of K in this particular case, and I'm given the concentration of one of them. I'm asked to find what the other one is. So the previous example, we were given all the concentrations, asked to find the value of K. In this case, we're given K and asked to find one of the concentrations given all the others. In this case, there are just two. So let's start off by writing what the K expression is. NO2 squared on top, N2O4 on the bottom. I'm looking for N2O4, so I need to do a little bit of rearranging. So in one fell swoop, I multiply both sides by N2O4 and divided both sides by K. You should work through that to make sure you're following along. So N2O4 is now equal to NO2 squared divided by K. Now I'm going to put the numbers in. So NO2 is 0.050 raised to the power 2 divided by the value of K, which is 4.6 times 10 to the minus 3. Sub in, and I get 0.54. So that's a very typical example of a problem, a numerical problem involving K, solving to find one of the components given the values of all the others. So in this particular case, we have three substances, and our equilibrium is NO-Br in the gas phase on the left, NO plus Br2 both in the gas phase on the right. We're given K. We're given two of the concentrations. We're asked to find the other one. So again, let's write our expression for K, which is products over reactants again. So concentration of Br2 times NO raised to the power 2 divided by NO-Br also raised to the power 2. So I'm looking for this. So again, a bit of quick rearranging. Multiply both sides by NO-Br squared. Divide both sides by K. So this is my rearranged expression for K. So the product's concentration divided by K. Sub in the numbers, which I made pretty easy in this example. So 1.0, 2.0 squared for the NO divided by 2.0. So that all falls out to be 2.0. But note, that's not the answer, because it was NO-Br squared. So I need to take the square root, which gives me the final correct value. So there are some pitfalls you can fall into. You can write the wrong expression for K, leave out the exponents, for example. You could get your rearranging all messed up, and then you might omit to take the square root. So plenty of opportunities to make errors in these kind of calculations. 23.5. So that's the key hint. Don't forget the exponents. They make a huge difference, not surprisingly, in the numbers you get. And moving through this quite rapidly. So now let's look at what happens when we have a system at equilibrium, but then start tinkering with it. So what happens to the equilibrium when changes are made? And that's where Chatellier's principle. Now this is entirely a qualitative thing. It's not a mathematical expression, but we can relate it to the mathematical expressions for K, and in almost every occasion it does work. So he says, if a stress is placed on a system at equilibrium, the system will respond by changing its position to minimize the stress. So that's what it states. So what does that mean exactly? Well, that's what we're going to take a look at. And what, anyway, are the things that you can stress? What stresses can be applied? We're going to look at 3. Composition. So we can change the composition by adding or subtracting reactants or products. We can change the pressure, and we can also change the temperature. So we're going to look at examples of those 3 stresses. So we can do 4 things to a system's composition. We can add a reactant, we can add a product, or we can take a reactant away, or we can take a product away. So 4 possible changes we can make. And essentially there are 3 possible outcomes, but in almost all cases actually just 2, but we've got to be aware that there is a possibility of a third. So most of the time the equilibrium will either shift to the right towards the products, or it will shift to the left towards the reactants. So those are the 2 main outcomes, but there is a third that we should be aware of. The equilibrium is unchanged, and that will occur in very limited circumstances. That normally won't crop up, but we should be aware of it. So let's have a look at how we're going to know which way it shifts, to the right or to the left. So let's have a look at an example. So here's that equilibrium. We looked at it earlier. HI on the reactant side, H2 and I2 are the products. So let's examine what happens if additional H2 is added. So if you add H2, momentarily you've got too much product for what the equilibrium wants to be. So the system will respond by trying to reduce the amount of H2 that you've added, which means that some of the H2 and some of the I2 are converted into HI, and the result is the system shifts away from the point of addition. So if I added a product, it shifts towards the reactants from right to left, as the arrow indicates. So if we can agree that that is logical, then all the other possible changes that you can do must follow logically. So if I added on the product side, it shifted to the left. So think, what's going to happen if I add on the reactant side? Using the same argument, the system will try to generate more products to reduce the amount of reactants you've added, so it will shift towards the product side or from the right. So if we're adding a reactant or a product, the shift will be away from the side that you add to. Now logically, we can predict what's going to happen when you remove a reactant or a product. So if the system shifted away from the side that you add to, surely it is logical that then it would shift towards the side that you remove from. So then if you removed a product, it would shift to the right. If you removed a reactant, it would shift to the left. So add products, it shifts to the left. Add reactants, it shifts to the right. And the converse is going to happen when you take them away. So then I did mention, what about if there's no change? How can that crop up? Because it seems like I covered all the bases. So the key point here is we were assuming in all of this that all of the components that we're adding or subtracting were in the gas phase or in solution. But if the substance does not appear in the expression for K, meaning it's either an S or an L, then adding or subtracting them has no impact. So it's a bit of a trick that instructors might want to play on you. They might give you an equation, an equilibrium, in which one or other of the substances is an S or an L, and ask you to predict what happens if you add or subtract them. And the correct response would be nothing happens because they're not in the expression for K. So these predictions only apply for G's and AQs, but 99% of the time, those are the equilibrium that you're going to deal with. So that's the rule for composition, changes, adding, subtracting reactants and products. Now we're going to look at pressure and temperature. And just to illustrate, in the Haber process, we have two reactants and a product. So this chart shows all the possible variations on the Le Chatelier theme. So we can increase the N2 on the left side, we can decrease N2, we could increase H2, we could decrease H2. Similarly, we could increase or decrease the product NH3. And this chart goes through all of the changes in the products and reactants concentrations for all of those 6 changes. I'm not going to go through it in detail, but all of them are consistent with the predictions of Le Chatelier's principle. So then here's an equilibrium expression, so there are 4 changes illustrated there. Which combination would result in the shift towards the products from left to right? So there are 4 possible answers. Let's pause the narration. I'm going to reveal the result on the next. The answer would be A, 1 plus 3. Increasing CO, a reactant, would shift it to the right, and decreasing CH4, a product, would also shift it to the right. So let's talk about pressure and equilibrium. It's a little bit of a different approach here. It's only going to pertain to systems that involve gases. If there are no G's in your equilibrium expression, there's no effect of pressure. So first of all, check out how many components are G's. If there aren't any, pressure is irrelevant. So normally there will be at least some G's, otherwise it's kind of a pointless question. So here's how it works. If the pressure increases, and it can also be written as volume decreases, when we get to talk about gas laws, we're going to learn that pressure and volume are inversely related, i.e. if one goes up, the other must go down. So under a pressure increase, the equilibrium will shift to make fewer gas molecules because fewer gas molecules exert less pressure. So here it's not necessarily about increasing pressure shift to the left or to the right. Does it shift to the side that has fewer gas molecules? That's the whole point here. And of course, if we do the opposite effect will occur. So pressure decrease, which is also equivalent to increase in the volume, the system will try then to make more gas molecules to make more pressure to make up for that deficiency. So the approach here is analyze the number of gas molecules on each side of the equilibrium. And we're going to find there are 3 possibilities. So 2 possibilities are there's more gas molecules on the left. Second one, more gas molecules on the right. Third one, the same number on each side. If that's the case, then pressure has no impact on the position of equilibrium. So going back to that example we looked at before, 2HI goes to H2 plus I2. Analyze the molecules. 2 on the left, 1 plus 1 equals 2 on the right. So this is an example where we would predict no change in the equilibrium if I change the pressure either up or down. 2 on the left, 2 on the right. No net change. However, in the Haber process, it's a different situation. We got 1 plus 3 equals 4 on the left, 2 on the right. So if I increase the pressure, I want to make it shift from the left to the right. And if I were to decrease the pressure, the opposite would occur. It would shift from the right to the left. So from a practical point of view, pressure has a big impact on the Haber process. And in fact, running the reaction at very high pressure is crucial for getting a sensible yield. And that represented some significant engineering challenges to developing the process. So a quick run through the impact of pressure there. Now let's have a look at temperature. And here we're going to have to treat the heat of the reaction as a product or a reactant, like it's a substance, which of course it's not, but for Le Chatelier, that's how we look at it. So let's take our Haber process again. N2 plus 3H2 goes to 2NH3. And that is an exothermic reaction. We talked about endo and exo before. So if I were to write the heat of that process, the energy given out, I'd write it as heat, a substance, in quotes, on the right-hand side. And now I'm going to change the temperature. And if I change the temperature up, increase it, you can think of that as adding heat or adding a product. Which way would the reaction shift? It would shift from right to left. So in an exothermic reaction, if we were to heat it or raise the temperature, it's like supplying a product. And so the equilibrium would shift towards the reactants to reduce the amount of heat made. So in the Haber process, actually, if I raise the temperature, I would reduce the amount of ammonia made. So the system, an exothermic reaction, would shift from right to left when you raise the temperature, and of course logically it would shift from left to right if I reduce the temperature. And of course logically, whatever is true for exothermic, the opposite would be true for endothermic reactions. So raising the temperature of an endothermic reaction would shift it towards the products, i.e. the outcome would be more favorable if you're trying to make something. So raising the temperature is a good thing. And of course then doing the opposite, cooling them would reduce the amount of products produced. So here's a system at equilibrium. This is actually a dissolving example, but it's exactly the same. So I got calcium acetate in the solid state on the left, and calcium acetate in solution on the right. It's an exothermic process. So what would happen if I were to raise the temperature or heat the solution? Which way would it go? Would A, increase the amount of calcium acetate solid, or B, decrease it? Think about it, pause the narration, answer on the next slide. And the answer is B. Heating an exothermic reaction would shift it to the left, increasing the amount of calcium acetate in the solid state. Overall, reducing the amount in solution, increasing the amount in the solid. So we've run briefly through the 3 different things you can do to upset a system of equilibrium: change its composition, change its pressure or volume, or change the temperature. This chart summarizes all the possible outcomes of playing with those 3 things. So in the composition side, we can do 4 things: add or subtract reactants, or add or subtract products. There are 2 possible outcomes. When we add, the system will shift away from, so if you add a reactant, it shifts to the right. Conversely, if you remove that reactant, it will shift to the left. And for the product, it's completely the opposite. So adding shifts away from to the left, whereas removing shifts towards, so the system will shift to the right, to the product side. Just to note that if the substance that you're adding or subtracting appears in the equilibrium as either an S or an L, then that's the situation where there is no change in the equilibrium when you add or subtract that substance. So that's the little trick there. Be on the lookout. If the substance is an S or an L, adding or subtracting it has no impact. Moving on to pressure, which could also be regarded as volume. So just to be clear, they're inversely related. So increasing P is equivalent to decreasing V and vice versa. So if I increase the pressure or decrease the volume, the system will shift to fewer moles in the gas phase. And of course, if I do the opposite, then the opposite is going to be true. So decreasing pressure or increasing volume will shift to make more moles. Just to remind, if the number of moles in the gas phase is the same on each side, then there's no effective pressure at all. Also, if there are no substances in the gas phase, then there's no effective pressure either. Finally, temperature. We need to do the analysis for endothermic or exothermic reactions. So in the endothermic case, we treat the heat as a reactant. Therefore, if we increase T, it shifts to the right. If we decrease T, it shifts to the left. And the opposite is true for the exothermic case. So if I increase the temperature, it shifts to the left, and decrease it shifts to the right. And that's pretty much the whole thing when it comes to Le Chatelier. So just a little question: which of these 4 systems would shift towards the products at lower pressure? Pause the narration, think it over, think about what you need to analyze, and we'll make the big reveal on the next slide. So the correct answer to that one was B. If I lower the pressure, I want to make more molecules, and in that particular case, I have 2 on the left and 3 on the right. So more molecules on the right side means the system will shift to the right if I decrease the pressure or increase the volume. So now we'll wrap up this chapter by looking briefly at rates of reactions and some of the factors that influence the rate. And this is based on a principle called collision theory, meaning that reactions don't happen unless molecules actually collide with each other. There's no long distance relationships in chemical reactions. The molecules actually have to collide. So underlying features: molecules are in motion. Molecules in motion undergo collisions. Collisions are necessary to make products. And a key point here is that only some collisions result in products. In fact, in most situations, the vast majority of collisions result in nothing happening. Only a small fraction actually results in products being formed. So there's a lot of futile colliding going along in most chemical systems. The temperature increases the molecule's energy, and that has an important influence on the fraction of collisions that result in products. So we showed this picture in an earlier lecture. Just let's review it. What we call the reaction profile, and just to remind, the vertical axis is the potential energy of the molecules, and the horizontal axis is something we call the reaction progress, meaning on the left hand side we begin as reactant molecules, and on the right hand side we end as products, and somewhere in between the system is converting from the reactants to the products. And in every case we can write what we call this energy profile, where the potential energy increases to a maximum and then decreases as we approach the products. So in any reaction, there's a reaction, a barrier, an obstacle for reactants to convert into products. So we call that the activation energy, the energy barrier over which molecules must make it. And they can supply the energy through their kinetic energy to mount the barrier. So the heat of the reaction is the difference between the reactants and the products, and that's what we could measure in calorimetry. But the determining factor in kinetics is the height of this barrier inside the box that has no impact on the overall energy change in the reaction, but has a massive influence on the rate of a reaction. At the very maximum, we call this the transition state, where the reactant molecules are in the process of being turned into products. So as I said, lots of collisions happening, but a great majority of them, in most cases, results in no actual products. So why is that? There are two factors. So one, the energy of the molecules. They've got to have sufficient energy to overcome the barrier. If they don't, they won't. And the second thing, which is perhaps more important in many cases, is having them oriented correctly. And this becomes much more significant when molecules are larger. If they don't collide in the correct arrangement, then the appropriate bonds cannot be made and nothing happens. So let's illustrate this concept with a very simple idea, like almost as simple as you can get. Two diatomic molecules. We've got a white diatomic and a green one. I mean, they could represent H2 and Cl2. And the products here are going to be HCl, which is one green one and one white one. So if they collide side by side like this, I think you can see the alignment is perfect for the new bonds to form between the H's and the Cl's, and the old ones between the H's and the Cl's here in the original molecules to break. So if they collide like that, that's perfect, provided the collision energy is sufficient. So if the two things are working, you're going to get product. But what if the orientation is incorrect? So let's say one of them collides head-on with the other molecule side-on, like this. Well, then the atoms are not correctly aligned, and that bond formation cannot take place. So the H2 and the Cl2 simply bounce off unreacted, regardless of the impact or the kinetic energies that they had when they collided. So orientation is an important thing. So let's just review. This is pretty straightforward. So if we increase the amount of reactants per unit volume, or the concentration, stands to reason, you're going to get more collisions per unit time. Chances are you're going to get more products formed per unit time. If you increase the temperature, you're increasing kinetic energy. So more molecules are going to have more energy, and that's going to increase the probability of them getting over the barrier, going to increase the rate. What I didn't mention yet but is a really crucial aspect in chemical reactions. The presence of a catalyst, which is a substance that speeds up the reaction, but is itself not consumed by it. So a catalyst is a very subtle way of increasing reaction rates without having to invest a lot of energy in increasing the temperature. And we'll look at a couple of examples of that. The fourth, which can be important, particularly in the case of solid reactants, the physical state. So think about it. You have a solid which has a very low surface area. Compare that with a finely divided powder which has a very high surface area. It stands to reason the rate of reaction is going to be much higher on the latter than on the former. So we're going to introduce an important concept of energies in molecules. So we know that the kinetic energy increases with temperature. But here's a key point that I haven't mentioned before. Not all molecules have the same energy at the same temperature. And what we're showing in the picture on the right is really a distribution of the energies. So let's look at this blue curve. So the energy is plotted on the horizontal, and the vertical axis is the fraction of the population that has that particular energy. So if I measure the area under this curve, that's all of the molecules in the population. So it's a general fact that very few have very low energy and very few have very high energy, and most are sort of somewhere in the middle. And you can look at a population of people, do a statistical analysis of their heights, for example, you'd find a similar pattern. Few are very short, few are really tall, most are somewhere in the middle. Now, if I raise the temperature, so the red line, the T2 is at a higher temperature, then this envelope spreads out. It's still very low at low temperature, but at low energy. But as I increase the temperature, I'm increasing the fractions that have energy at a higher quantity. The area under the curve is the same because I've not changed the overall population. So here's a key point. I made a vertical line here that's equal to, say, the activation energy of the reaction. So the molecules must have sufficient energy to get over it. But if their energy, their kinetic energy, falls below the barrier, they will not succeed. But if their energy is above the barrier, then they can, provided the orientation is correct. So one key outcome is the area under the curve that has sufficient energy increases dramatically with temperature. So for our red population, it's way bigger than for the blue. So that's how we can explain why increasing temperature always increases the rate of reaction, because it increases the fraction of molecules with sufficient energy to get over the barrier. So I'm calling this the brute force approach. You just heat it up, it's going to go faster. A catalyst, I'm calling that the cunning way, because we're not increasing the molecule's energy, but instead we're tinkering with the barrier. In effect, the catalyst reduces the energy barrier, making it easier for the same population of molecules to get over it. So we can illustrate the example with one very important reaction that was responsible for the creation of the ozone hole in the stratosphere, which became a massive environmental concern beginning in the mid-80s. So this shows the reaction of ozone, which is O3, to make O2 oxygen. So as two O3s become three O2s. In the absence of a catalyst, you've got an energy barrier, which maintains that rate of decomposition at a relatively low rate, let's say. Now, if I introduce into the O3 population a single chlorine atom, which could be obtained by the decomposition of molecules that were called chlorinated fluorocarbons, or CFCs. These chlorine atoms are fantastically efficient catalysts for converting O3 into O2. And the way that happens is that the energy barrier is changed. It actually lowers the height of the barrier. Thus, more O3s under the same conditions can convert into O2s. And therefore, that's how the ozone hole became, because the ozone started disappearing faster than it had previously. Now, there's a lot more to this story than I can share in this single slide, but it's a good illustration of the principle of catalysis. We can do the same thing, similar sort of ideas, in the conversion of exhaust gases from automobiles. So in the bad old days, some of the products would be things that would be not good for us: carbon monoxide, nitrogen dioxide, unburnt hydrocarbons, nitric oxide. All of these things not good for our health or that of the environment. Think brown smogs over Los Angeles. Introduce a catalyst, on the other hand, the products become nitrogen, water, and CO2, all of them comparatively benign. Of course, you're going to say, well, CO2, responsible for climate change, bad, but it's a heck of a lot better than any of these products. So the principle of the catalytic converter in your car is that it provides this metallic thin layer over a large area that the molecules adhere to briefly, but long enough to make the conversion of the undesirable products of the exhaust into more desirable ones. And perhaps in living systems, there's nothing more important than enzymes to make our organisms work efficiently. So an enzyme is a biological catalyst. And most of their large proteins, and this little animation on the right hand side is really illustrating one of the concepts of the action of an enzyme. So I said the orientation is very, very important, particularly when you have large molecules. So the enzyme in this little animation is serving to bring the substrates, the reactants, into the enzyme, get them oriented correctly so that the products happen. So that is a brief illustration of different types of catalyst. So we'll wrap up. What combination of these factors would increase the reaction rate? So we've got four things: increasing the SO2, lowering the temperature, adding a catalyst, or decreasing the SO2. So there's one combination of two that's correct one. Pause the narration. We'll reveal the answer on the next slide. And the answer is B. Adding a reactant would normally serve to increase the reaction rate, and adding a catalyst, lowering the energy barrier, will also achieve the same end.